Hi learners. From the chapter Application of Derivatives, today we shall learn the topic Increasing and Decreasing Functions. What calculus can do with such functions, we shall study in detail.
Let us consider the marks scored by a student in successive unit test conducted in June, July, August, September, October, November. When we consider the marks scored in July, that you can see that is 18 marks here, and in August you can see that is 20 marks. Means the curve is going up, means the student is making progress. So if you take this point as a x1 and this as s2, which are the 2 points in the domain of the function where x1 is less than s2, then here you can see f of x1 means a mark scored in July, that is f of x1, and f of s2 means a mark scored in August, then that will be less than or equal to here. Why the less than or equal to? Because sometimes for example, in the month of August and September, the student is having the same marks. But you can see that once he scored 20, next time he is not going below than that. That is, at least he is keeping the same marks, but not going down. Similarly, you can see that if it reaches a particular height, say for example 26, then it is not going down. It may not go up, but it is not going down. That is why I am saying whenever x1 less than s2, f of x1 less than or is equal to f of s2 here. So if you consider this interval from June to November, you can see that for any 2 points x1 and s2 in the domain, whenever x1 less than s2, we can see that f of x1 less than or is equal to f of s2. In such a case, we say that the function given is a increasing function. Function given is a increasing function. Then, on the other hand, if the performance of the student is like this, here you can see if any 2 months we take like this x1, s2. Again x1 less than s2, but it implies the performance, that is f of x1 is greater than or is equal to f of s2 here. For all x1, s2 in the interval, say right from June to November here you can see. That is, whenever x1 less than s2, f of x1 greater than or is equal to f of s2, means the progress in a particular month is always better than the progress in the succeeding month here. It may be better than or at least at par with the performance. For example, here you can see that this performance, that is 18 marks in the month of July, and in August that is also 18. But once he achieved 18, next time he is not going up, means not getting more marks than 18. It may be at par with 18 like this. So that I am telling you, whenever x1 less than s2, then which implies f of x1 is greater than or is equal to f of s2, then we can say that the function is a decreasing function. F is a decreasing function here. F is a decreasing function. Now you can see the graph here. Here if you choose the point x1, s2, of course x1 less than s2 only. And fx1 is strictly less than f of s2. There is, you can see that for this red branch of the graph, that is from here to here, you can see that whenever x1, s2 is such that x1 less than s2, you can see that f of x1 is strictly less than f of s2. If it happens, we can say the given function is strictly increasing. Given function is a strictly increasing, we can say, strictly increasing function. One more thing we can see here. You can see now from this point, say A, to this point, that is the red portion finishes. So for this open interval AB, if we consider any point on the curve and if you draw the tangent at that point, you can see that the tangent is having positive slope. You can see that the tangent is having positive slope. Positive slope means derivative dy by dx is positive, because according to geometry, slope, and according to calculus, derivative. According to geometry, slope of the tangent means derivative that is in calculus. So there is a close connection between that. Now here you see when x1 s2, here again you can see x1 is less than s2 only. But at the same time, the height fx1 and fs2, if we consider, you can see that fx1, that is the value of the function at x1, is greater than, strictly greater than f of s2. Then if it happens in a function, we can say that the function is strictly decreasing. So here on the graph, this green portion of the graph is having the strictly decreasing nature. I told you this red portion is having the nature strictly increasing, and this green portion is having strictly decreasing, and again this blue portion will have the nature strictly increasing. And here again, if you consider the tangent, that is this green portion, I told you that is a strictly decreasing nature. And if you consider any point from that interval, what is happening, you tell me. If you consider any point from that interval, what is happening? Slope is negative. Slope is less than 0 means derivative is less than 0. So this is very simple and easy to understand. Whenever the derivative is negative, we can see that that function or portion of that function, or portion of the graph, will be decreasing, strictly decreasing here like this. Otherwise, it will be strictly increasing if the tangent is having positive slope. If the tangent is having positive slope, you can see then the function will be increasing, and if the tangent is having negative slope, you can see that the function is decreasing.
Let us consider the graph of a function which is going up, then coming down, then again going up like this. The green portion alone, that is going up. The blue colored portion is going down, whereas the red colored portion is going up. Now you can see at every point on the green colored portion, the tangent is having a positive slope like this. Tangent is having positive slope means, what do you mean by tangent slope? That is derivative. So derivative is positive. So if derivative is positive for a branch, we can see that that portion is increasing like this. That is, tangent is having a positive slope. Tangent having positive slope means derivative positive. Therefore, the green portion is increasing nature, whereas the blue colored portion, that is going down, so that is having decreasing nature. Tangent is having negative slope means that is derivative is negative. So because tangent's slope is what is called a derivative, then you can see that the red colored portion again, that is going up, and you can see that tangent is having positive slope. Tangent is having positive slope means derivative positive. So this way we can identify by means of calculus the increasing, decreasing nature of a function.
So remember that if the function defined on the interval I, and if you take 2 points x1, s2 from that interval, Then the case 1, x1 less than s2 implies f of x1 less than or is equal to f of s2. We do say the function is increasing. On the other hand, if x1 less than s2 implies f of x1 is strictly less than f of s2, then we can say the function is strictly increasing. We can say the function is strictly increasing. Then again, if x1 less than s2 implies f of x1 greater than or is equal to f of s2, then we can say the function is decreasing. And the last case, when x1 less than s2 implies f of x1 greater than f of s2, that is f of s2 is strictly less than f of x1, then we can say the given function is strictly decreasing. And according to calculus, strictly increasing means derivative is positive, and strictly decreasing means derivative is less than 0. Now here consider the function f given by 3x minus 5, that's a straight line, and you see it is definitely a strictly increasing function. Why it is so? That is very simple. If we choose any 2 points, say for example here and here, and if you compare their height, means functional value, you can see that f of x1 is strictly less than f of s2. So you can see that is the function is a strictly increasing function. But at the same time, calculus can help you without drawing this graph and looking whether fx1 less than fs2 every time. So that will be time consuming process also. Here simply you take the function, then find f dash x. You see that is 3 and 3 is positive, and derivative positive means function is strictly increasing. So you can have it very simple way like this. Now consider the function f given by f of x equals x cube minus 3x squared plus 4x, where x of course is in the set of real numbers, because we know that the domain of a polynomial is the set of all real numbers. That is very clear. And here we need not draw the graph and compare the fx1 value, fs2 value in order to see whether the function is increasing or decreasing. No need. That is time consuming, as I told you. You go for simply f dash x, that is derivative, that is 3x square minus 6x plus 4, that you can see. And here this could be written as 3 into x square minus 2x plus 1, then again a plus 1 we can write, because we have to adjust a 4 there. So that is equal to 3 into x minus 1 the whole square plus 1, and you can see this quantity is strictly greater than 0, because being a square, the minimum value of this square is 0 only. So plus 1 is there, therefore this total quantity, total value f dash x will be positive. That is f dash x positive means but you can conclude that is function is increasing, strictly increasing. Function is strictly increasing. Now let us consider the function f given by f of x is equal to cos x, where x is in the interval say 0 pi. We have to see whether this function is strictly decreasing in 0 pi. Here we have to see whether this function is strictly decreasing in the given interval, that is 0 pi. So how to prove it? So we have to consider derivative, as I told you, that is negative sin x. And you see for all x belongs to 0 pi, that is you can see 0 is here and pi is here. So 0 to pi means first quadrant and second quadrant. And in first and second quadrant, all trigonometric ratio positive. Therefore, sign is positive there. Sign is positive. And in second quadrant, sine and cosecant, they are positive. So, simply speaking, throughout the first and the second quadrant, what we can conclude, sin x is positive. So, negative sin x is positive, but negative sin x is there. Therefore, the total value of the derivative f dash x will be negative for this open interval 0 pi. Therefore, the given function is strictly decreasing on the given interval. What is it? That is 0 pi. So it is very simple to prove. Then again you can verify the same function given by fx is equal to cos x. What about pi to 2 pi if we consider pi to 2 pi interval? That is x belongs to this open interval. This is our interval, I4 interval here. Then you know f dash x that is equal to negative sin x only. Then what about the interval that is pi to 2 pi? Pi to 2 pi means we are to consider the third quadrant and the fourth quadrant. In third and the fourth quadrant, you see the sine value will be, the sine value is this depth here. So here it is, this is what is called the sine value here. Similarly, here also you can see sine value becomes a depth only. So that is negative. So sin x is negative. Sin x itself negative means negative sin x will be positive. Therefore, negative sin x that will be positive, you can see. So simply speaking, derivative is positive for all x belongs to pi to 2 pi here. So you can conclude that the given function is strictly increasing on the given interval pi to 2 pi. Is it very simple? Yes, it is. Thus, we have seen that for the interval 0 to pi, the function was strictly decreasing, and for the interval pi to 2 pi, it is strictly increasing. Then, if we consider the total interval that is from 0 to 2 pi, what about the nature of the function? We can see that for some portion it is that is up to pi. From 0 to pi, you can see it is a decreasing nature, and from pi to 2 pi it is increasing nature. So we cannot say for the throughout interval 0 to 2 pi, for the total interval 2 pi, we can say that function is neither increasing nor decreasing. That means we can't say whether it is increasing or decreasing for the total interval 0 to 2 pi. Now consider the function f given by f of x is equal to a polynomial function 6 cot minus 5x plus 6. For the polynomial function, the domain is negative infinity to plus infinity. The open interval means the set of all real numbers. So we have to divide this total interval, that is open interval negative infinity to plus infinity. We have to divide this interval into portions, into subdivisions, in which the function is increasing and in which subdivision of this interval function is decreasing, like this. So what we shall do is, we shall find the derivative, that is f dash x, that is equal to 2x minus 5. And you see that whenever the function is changing the nature, that is derivative is sometime positive then negative, then when it is changing, so we see that there may be some 0 point, that is derivative may be 0 at that point. So let f dash x is equal to 0. Then you can see that 2x minus 5, that's our f dash x, that's equal to 0, means x equal to 5 by 2. That means the total interval that is from negative infinity to 5 by 2 function may have some nature, and from 5 by 2 to plus infinity function may have a different nature. That means we have to check it. How to check it? That is simple. That is case 1. Our interval is open interval negative infinity 5 by 2, and let x belongs to this interval, that is negative infinity 5 by 2. Actually, this is the technical meaning about intervals. But what is the ordinary meaning? X belongs to this interval means it is nothing but x less than 5 by 2. That's all. For any x in this interval, that must be less than 5 by 2. So which implies 2x will be less than 5. So which implies 2x minus 5 will be less than 0. And you see, what about this 2x minus 5? This 2x minus 5 is nothing but our derivative f dash x. So f dash x is negative in that interval. F dash x is negative in this interval means the given function is decreasing, strictly decreasing in this interval negative infinity to 5 by 2. And now as a case second, you can see that is for case second, that is 5 by 2 to plus infinity. Let x belongs to this interval, say 5 by 2 plus infinity. Means the ordinary meaning is x will be greater than 5 by 2 this time. You know, for any x value in this interval, x will be greater than 5 by 2. So which implies 2x must be greater than 5. So which implies 2x minus 5 will be greater than 0. And then what about 2x minus 5? That is nothing but derivative f dash x. So we could prove that derivative is positive in this interval. Therefore, the function is strictly increasing in the interval 5 by 2, open interval 5 by 2 to plus infinity. So this way we can separate the given interval into subdivisions, so that in which subdivision the function becomes strictly increasing, and in which subdivision the function becomes strictly decreasing, we can identify. Let us consider another problem. Y is equal to log 1 plus x minus 2x divided by 2 plus x, where x is greater than negative 1, is an increasing function of x throughout its domain. So how to proceed with? I told you we have to find y1 means a derivative, that is dy by dx, that is equal to. So we have log 1 plus x means that is 1 by 1 plus x, then derivative of 1 plus x, that is 1 only. We are using chain rule, then minus, we have to apply quotient rule here, that is v, that is 2 plus x into u dash means 2 minus u into derivative of the denominator, then divided by 2 plus x the whole square. That can be simplified as 1 by 1 plus x minus 2 into 2 4 plus 2x minus 2x, then whole divided by 2 plus x the whole square. Now what will happen? That is equal to 1 by 1 plus x minus 4 divided by 2 plus x the whole square. We can make the denominator common, that is 2 plus x the whole square minus 4 into 1 plus x the whole divided by 1 plus x into 2 plus x the whole square, which can be further simplified as 2 plus x the whole square means 4 plus 4x plus x square minus 4 minus 4x, isn't it? Whole divided by 1 plus x into 2 plus x the whole square. So here you can see that this plus 4 minus 4 plus 4x minus 4x getting cancelled, and we have dy by dx equal to x square divided by 1 plus x into 2 plus x the whole square. Now let us analyze. We are given x greater than negative 1, means x plus 1 is positive, and which implies x plus 1 plus 1 greater than 1. So x plus 2 is greater than 1. We have two informations here. So x plus 1 is positive, means this term will be positive, and here x plus 2 is a number greater than 1, then square of it means that is positive, and here x square will be greater than or is equal to 0. Minimum value of a square number can be 0, and here x is greater than negative 1 only. So x can be 0, so x square can be 0 in that way. So simply speaking, we have dy by dx is greater than or is equal to 0, means the given function is we can say increasing. We cannot say here strictly increasing because equal to 0 is also so we can say that f is increasing. That's a demand. So we could prove that the function is increasing throughout the domain. Increasing throughout its domain. Okay. That's all for now. We shall come up with some other topic next time. Thank you.